Afternoon, folks. I hope everybody is doing well. This is part 2 in my lecture series on science in the 20th century. If you have not already watched part 1, then I would recommend you go back and do that now so that you have some foundational information for what's to come. Also, if you were in my history of science class and you've not already done so, you might want to go on Blackboard and acquire the summary notes with names and dates and so forth for this lesson to follow along with. Now, first half of this, we talked largely about the backdrop of 20th century science, the guiding principles behind it, the professionalization, the establishment of the scientific paradigm as the default global paradigm, the intrinsic relationship between science and war that we're going to see throughout the 20th century. And we talked about the accomplishments of such diverse people as Nikola Tesla, Albert Einstein, Marie Curie, and the various nuclear scientists involved in such things as quantum mechanics and the Manhattan Project, people like Niels Bohr, Werner Heisenberg, Robert Oppenheimer, Ernest Rutherford, and a few others. We got through World War II, but let's backtrack a little bit and talk a little bit more about what else was going on in the science of World War II, because it was not all about the atomic bomb. Numerous other domains of modern science were being born during this time. Now, arguably, one of the great technological terrors of World War II was going to be the rockets used by the Nazis to assault London and other cities. The Blitz, I'm sure you're aware of, the bombardment of the city of London with rockets during the war, is considered one of the great and terrible events of the European theater of World War II. Nazi rocket science was second to none during that time period. The Germans were far ahead of us in terms of building military rocketry. And much of that development can be attributed to an engineer by the name of Werner Magnus Maximilian Freiherr von Braun. That's about the most German name you can imagine, right? More often you just hear a shortened form of his name, Werner von Braun. Von Braun is a title of nobility. He spells Werner differently than Heisenberg, incidentally. Werner Heisenberg was W-E-R-N-E-R. Werner von Braun is W-E-R-N-H-E-R. Von Braun, lowercase von, V-O-N, capital B-R-A-U-N. Werner von Braun. He was the Baron von Braun, Freiherr von Braun. Born in 1912, died in 1977. Von Braun was a physicist and engineer, pioneer in rocket science, who has the rather extraordinary resume of having been both the head of German rocket research during World War II and later the chair of NASA. Now, von Braun was born in the German region of Prussia. He was fascinated from engineering and rockets from a young age. When he was 12 years old, he actually set off a wagon covered in fireworks in the middle of a crowded street and was briefly detained by the police for that experiment. When he was 16 years old, he read a book by a fellow by the name of Hermann Oberth. Hermann, H-E-R-M-A-N-N, Oberth, O-B-E-R-T-H, one of the pioneers of rocket science. Oberth was born in 1894, died in 1989, and is most famous for conceiving of the multi-stage rocket. Oberth, in his book, was going to introduce the idea that a multi-stage rocket, providing additional thrust once you had gotten high enough, could potentially lift a rocket out of Earth's atmosphere. And thereafter, von Braun was obsessed with the idea of space travel. More than anything else, von Braun wanted to break the boundaries of our planet. He wanted to put humans into space. He wanted to get humans to the moon. He wanted to get us to Mars. Von Braun dreamed of exploring the great reaches of the universe. Now, he eventually went to the University of Berlin, got his doctorate there after studying rocketry under Oberth, who was his mentor there, and proved to be very impressive even as a student. After he completed his degree, he was almost immediately recruited by the German military for rocket research. Now, as you probably gathered, in the lead up to World War II, there were a lot of American scientists corresponding with their European counterparts, and German scientists were no exception. You saw, for example, a lot of Ally and Axis collaboration, or people who were in the Allied countries and Axis countries, a lot of whom didn't care much about the war, they just cared about their science. You saw, of course, Niels Bohr and Werner Heisenberg had their very famous relationship that crossed boundaries of nation and ended up causing some trouble for the two men. Well, von Braun is no different. He's going to become very good friends with an American rocket pioneer by the name of Robert Goddard, Goddard. Goddard was born in 1882, died in 1945. Goddard is famous for launching the first liquid fuel rockets in 1926. Now, Goddard and von Braun had lively letters with each other talking about their various rocket research. Both of them benefited considerably from each other. Till finally, in 1939, growing military tension led both sides to basically say to them, hey, maybe you should cut out with sharing your technology with the enemy. Now, America never really adopted any of this. Goddard, for his part, tried really damn hard to get America interested in rocket research in the lead up to World War II, and he went to the Department of Defense and he's like, hey, rockets, they might be really good for war. And the Department of Defense was like, eh. And Goddard came back a few years later and said, you know, my buddy Werner von Braun in Germany says that the Germans are building military rockets. Maybe we should think about doing that thing. And the Department of Defense said, not interested. And later he said, this is happening. We're about to get into a war with people who have rockets. Can I make you some rockets, please? And the Department of Defense said, not interested, and instantly stopped talking to von Braun. You're telling him too much about how to build rockets. At which point, Goddard basically threw up his hands and gave up, became a farmer, became an alcoholic, and died in 1945. But much of the knowledge that he shared with von Braun ends up being very important to the German war efforts. Von Braun is a brilliant engineer, and he is designing rockets for the Nazis as the thing he has to do. He has not lost his interest in space travel. Von Braun wants more than anything else to put humans into space. He is a member of the SS because all the top military officials in Germany are, but he is not happy about it. Von Braun does not care one whit about the war. He is unhappy with the conditions of the slave laborers that are forced to build military hardware for the Germans, and actually gets in trouble on more than one occasion for treating them more kindly than his superiors thought that he should be. Von Braun wants to go to space. And continually, throughout the lead up to World War II and even during World War II, again and again, he attempts to divert resources away from military rocketry and towards space rocketry. And time again, the Germans keep telling him, no, get back on the military rockets. And von Braun sees this as the price he has to pay to make his dream happen. So he works on these things. He ends up designing a lot of rather amazing technologies. He assembles the first liquid fuel engines for jet-assisted takeoff of aircraft. He creates the first anti-aircraft missiles, the first A4 ballistic missiles, the Aggregat 4, better known as the V2 rockets. You've probably heard of that. So he's making some amazing rocket weapons for Germany. Of course, this is all terrible because the Nazis are raining them down upon innocent people, and it's not going so well. Von Braun is deeply frustrated with the war. He tries to make moral objections to the use of this technology, but there's nothing at the end of the day that he can do about it once he's created it. Whenever it was reported to him that the V2 rockets had successfully hit England in September of 1944, von Braun commented, the rocket worked perfectly, except for landing on the wrong planets. His constant moralizing and protests against the conduct of the research and the uses of this research got him accused of communist sympathies and of sabotaging the rocketry program from within. He was actually briefly arrested for this in March of 1944 and detained for 2 weeks on possibility of treason to Germany. Ultimately, however, he was personally released when Hitler said he was indispensable to the war effort and ordered him to be cut out of prison. But at this point, von Braun knew he was not going to be allowed to do the work that he wanted to do. He knew that his production was going to continue to be putting out weapons that he was morally opposed to, and he realized that he was going to have the Nazis breathing down his neck from that point on. And at that point, Wernher von Braun decided the time had come to surrender. So he began working out a secret plan. In 1945, von Braun goes to the head of the SS in Germany. And he says, hey, the Allies are getting deeper and deeper into our territory. They knew who I am. They knew who my research team is. They're going to want us. They're going to want to capture us, and they're going to make us surrender the technology if they do capture us. You don't want us falling into Allied hands. I got an idea. I'm going to take my research team. I've got a chalet up in the Alps. We're going to sneak my whole research team out of Germany, go up to that little chalet, and hide out there. The Allies will not know we are there. We can wait out until, of course, great old Germany defeats everybody, and then we can come back and everything will be cool. And the head of the SS says, yeah, okay, sounds like a pretty good idea. And so von Braun prepares his team to go hide out in the Alps. An entire science team leaves German research to go to Bavaria and hide in the mountains. What von Braun did not tell the SS was that he had made secret arrangements with his brother-in-law, who was an Allied sympathizer, to alert the Americans as to his location. What von Braun did not know is that the SS guards who went with his men were under strict orders to kill all of them if the Americans got close. Well, as it happened, they settle in. They are in that little chalet. On May 2nd, von Braun gives the signal to his brother-in-law, who rides a motorcycle into the middle of an American encampment in the middle of the night, beeping the horn and shouting, I am Wernher von Braun's brother, and he wishes to surrender. The Allies make a lightning raid on the chalet. Remarkably, none of the scientists are killed. The Nazi guards were taken by surprise. And thus, Wernher von Braun and his entire research team surrender to the Allies. And as part of a project known as Operation Paperclip, named for the colored paperclips put on the files of the scientists involved, a number of German scientists are smuggled out of Germany and to the United States to contribute their work to the American war effort. Von Braun arrives in America in September of 1945, about a month after the surrender of Japan. The war is over, and he is now under house arrest in the United States as a top Nazi scientist. They're confining him to Fort Bliss, Texas. Sorry, Fort Bliss, Texas. There we go, Fort Bliss, Texas, where he is promptly put to work on building military rockets for America. This was not the way he wanted things to go. Now, von Braun toes the line. He behaves well. He has no loyalty to Nazi Germany. He is happy to not be working for the Nazis anymore, although he still wants to do space research. And throughout the latter half of the 1940s, he continues building military rockets for America. In 1950, he is finally permitted to leave Fort Bliss of his own recognizance. He is released into the country as, a free man. He becomes a United States citizen in 1955 and never returns to Germany. Now, throughout the 1950s, von Braun is continuing to build military rockets for the U.S. military, but he is also working on his space travel projects. He creates designs for manned missions to the moon and Mars, for a space station, and even for a moon base. Time and again, von Braun endeavors to interest the United States in the things he is pursuing. The Cold War is well in session. You all know this by now. The Cold War rages throughout the latter half of the 20th century as Russia and the United States, or I should say more USSR, the Union of Soviet Socialist Republics and the United States, are staring down each other awkwardly across the globe and waiting for somebody to make a bad move. There's a lot of one-upmanship with military technology, building bigger and bigger and more nuclear weapons. and trying to outdo one another in the scientific and military theaters. Now, we all know, of course, about the space race, the efforts to be the first nation to put humans into space and to put humans ultimately on the moon. Now, here's the thing that might be hard to believe, that in the early 1950s, the space race was not yet a thing, that the United States had not gotten the memo. We had not decided yet that the pursuit of outer space as the next frontier of research was going to be a good thing to do to compete with the Soviet Union. Von Braun pushed and pushed, but he could not interest America in space travel. He actually ended up partnering with an American filmmaker, a fellow you've probably heard of by the name of Walt Disney. Von Braun and Disney produced a series of educational videos and shorts that played before Disney movies in American theaters throughout the 1950s, glorifying the idea of space travel as the next great human adventure. Disney himself became so fascinated with the idea that he insisted on a space-themed area installed in his first amusement park, Disneyland, called Tomorrowland. Now, Von Braun had succeeded in getting the word out to the public. He interested an entire generation of school kids in the idea of space travel and space exploration as a super exciting thing. But the US government had still not bitten on the bait. Until October 4th of 1957. Now, those of you who are space nerds know what happened on October 4th of 1957. You know? No? Okay. What happened on October 4th of 1957 is that the Soviet Union launched a satellite known as Sputnik 1. S-P-U-T-N-I-K. Sputnik. Sputnik 1 was not a terribly impressive satellite, but it was the first satellite to go into a stable orbit around the Earth. Sputnik 1 was about the size of a grapefruit and basically went beep. It was not really a really exciting piece of instrumentation. It was certainly not a weapon. But it could be seen in the sky, twinkling in the night, a new mobile star flying over American soil. A Russian object put up so high that none of our weapons could get to it, and flying over our heads. And the United States was collectively terrified. My father, who spent his career as a nuclear chemist, remembers his father, who was himself an electrical engineer, taking him out into the backyard at night and pointing up and showing him the Sputnik satellite flying overhead and saying things like that are going to kill us one day unless you learn a lot more science. And my dad spent his life working for the Department of the Navy doing nuclear chemistry. And incidentally, my father and my grandfather, they got a cat that year, a kitten. They named her Sputnik because she was all black with one little bright spot of white on her fur, like the satellite flying overhead. But anyhow, though, so Sputnik goes zooming by. And now the government is interested in space. And they go to Von Braun and they're like, okay, so space travel. Can you make us something for that? And Von Braun, who has already been building plans for this, says, I'll do it for you, but I want to put a man on the moon. That's his condition. He wants to do the moon research he's always wanted. Von Braun was already nearly ready. January 31st of 1958, just a scant 3 months after the launch of Sputnik, Von Braun launches the Redstone rocket, carrying Explorer 1, the first American satellites. Later that year, the National Aeronautics and Space Association, or NASA, is established. Von Braun agrees to work for NASA only if he is permitted to undertake the Saturn rocket program, the program dedicated to human space travel. He becomes the first director of NASA in 1960, holds that position until 1970. Now, during the course of the next decade, the space race is full tilt. The Russians do beat us to putting people in space. The Yuri Gagarin, you might know that name, is the first cosmonaut or Russian astronaut to break Earth's atmosphere. But the United States, not far behind. We begin putting people first up in the atmosphere, then into orbits. Little by little, von Braun is improving his rockets, improving his probes and his technology, and laying the foundations for the research that will ultimately get mankind beyond the limits of our planets. The Apollo project is launched throughout the 1960s at the instigation of President John F. Kennedy in an effort to put an American on the moon before Russia can do that thing. There are several Apollo missions that don't get off the ground. There are several accidents in which people die in launch attempts and so forth. Russia has a bunch of mistakes like that too, way more than we do. Russia was in many ways working faster and more dangerously than we were, and they lost a lot more cosmonauts than America lost astronauts in the early days of exploration. A lot of this effort, I should point out, was facilitated with the help of female mathematicians and programmers, engineers who were doing the patient coding work necessary to get a rocket precisely to the moon and back. A lot of very famous women were involved with this. The programming of the day, the computers that were used to take people to the moon had less power than the computer in this device right here. But the programming books that powered them were still stacked up taller than the programmers who wrote them. And a lot of those programmers were women. Some of you might be aware of a book and a more recent movie called Hidden Figures about a number of African-American mathematicians, among them a woman named Katherine Johnson, whose calculations were critical to the success of the moon mission and who were actually considerably better than their male engineering colleagues in a lot of the math involved in the Apollo mission. And we owe them a great debt of gratitude. Katherine Johnson passed away just a few months ago at the age of 101, and her story is well worth the reading. Go read Hidden Figures. It's an amazing book. Now, ultimately, the Apollo mission paid off. On July 20th, 1969, Apollo 11 made a successful approach to the moon and dropped off the first lunar landing module, the Eagle, which landed on the surface of the moon to the famous statement, "The Eagle has landed." There were 3 astronauts on that mission: Michael Collins, Buzz Aldrin, and Neil Armstrong. Probably know those names. Collins was not interested in setting foot on the moon. He was actually kind of frightened of it. He stayed to pilot the launch module that remained in orbit, waiting for the return of his colleagues. Buzz Aldrin and Neil Armstrong went down in the 2-man probe to land on the surface. They drew straws to see who got to be the one for the great honor. Neil Armstrong won that. And thus, on July 20th, 1969, while the world watched on live television, Neil Armstrong became the first man to set foot on a celestial body other than Earth. You're probably all aware of his famous words that he said at the time. That's one small step for man, one giant leap for mankind. He actually flubbed it. He had wanted to say that's one small step for a man, one giant leap for mankind. But he messed up the wording in the moments, and he kicked himself for the rest of his life because he was kind of a grammar nerd and he didn't like that he messed it up. But we had done it. Over the next several years, NASA launches a total of 6 missions to the moon, 5 of which are successful. Of course, the infamous Apollo 13 mission does not successfully land on the moon, ends up having a rocket failure. They end up slingshotting around the moon, getting a gravitational assist from the moon to get back to Earth, and manage to return with all the astronauts on board alive whenever it was thought they were going to be lost in space forever. They still hold the record as being the human beings who have been the furthest from Earth ever for that slingshot operation around the moon. But NASA lands 5 missions on the moon between 1969 and 1976. But following the conclusion of their first moon mission, as far as the US government is concerned, we've won the space race. And a lot of interest is lost. Von Braun wants to push further. He wants space stations. He wants Mars probes. He wants to land people on other planets. But he is unable to interest NASA in a more ambitious mission. Ultimately, he resigns his commission 1972, a bit frustrated by this, dies of kidney cancer just 4 years later. But his legacy lives on. Von Braun's design is now in use, albeit in improved and modified form, for the International Space Station. And now we are talking, for the first time seriously in years, about putting together a manned mission to Mars and returning to the moon for the first time since the 1970s. Incidentally, the Russians did get to the moon as well. To date, Russia is the only country other than the United States who has ever put human beings on the moon. One Russian mission succeeded in doing so in the early 1970s. Although now there are several countries talking about manned lunar missions, including, among others, China, India, and the European Union. Now, part of all of this, part of what made all this possible, was having the tech to navigate there. And that included a thing called a computer. Now, the computers of this day were not impressive. Like I said, the computer that got us to the moon had less power than your smartphone. But computer science is being born at this same time, and it is also a product of World War II. And we can lay much of the story of computer science and its success at the feet of a rather remarkable British mathematician and cryptanalyst by the name of Alan Turing, Turing. Turing was born in 1912, died in 1954, native of London, and is often considered the father of modern computer science. Turing was an enthusiastic schoolboy. He once biked 60 miles from his home outside the city to attend the first day of school when there was a general strike that shut down the rail lines. He was mathematically gifted even from a young age. By the time he was 16, he was grasping Einstein's general theory of relativity at a level that many professional physicists could not. He studied mathematics at King's College in London and began working on the idea of computational machinery. In 1936, Turing, at the age of 24, suggests the concept of a machine capable of performing any conceivable computational procedure as represented and fed to it in the form of an algorithm, what is now referred to in computer science as a universal Turing machine. And this is the concept vital to modern computer science of so-called universal computation, namely that a computer can do any operation that you tell it how to do. Turing traveled to the United States to finish his doctorate in mathematics. He worked under Princeton mathematician Alonzo Church, born in 1903, died in 1995, in developing a lot of the principles necessary to modern computer science. Concepts of universal computation, definable real numbers, algorithms, and of course the famous Church-Turing thesis, which is the basis of modern computational theory. Turing gets his doctorate under Church at Princeton. By the time he's done there, he has developed the concepts of ordinal logic and relative computing, sometimes called Turing reduction, in modern computer science. And he's gotten interested in the obscure mathematical study of cryptanalysis, or code breaking. He returns home to England, and during World War II, begins working as a code breaker. He is employed at a secret research park outside of London called Bletchley Park, B-L-E-T-C-H-L-E-Y, and specifically in a building at Bletchley Park known as Hut 8. It was known to be a research center, but nobody knew what they were actually doing there, because Bletchley Park was the site where the Allies were desperately trying to break German codes. The Nazis had developed a fiendishly complex mathematical code called Enigma. The Enigma code, E-N-I-G-M-A, was coded using a machine, an Enigma machine, which devised a unique coding sequence for every signal, and therefore was exceedingly hard to break, unless you had another Enigma machine to work with. Now, Turing and a bunch of fellow scientists, many of whom were Polish mathematicians and cryptanalysts who were refugees from Nazi-occupied Poland who had come to England to help out with the war efforts. Turing and his colleagues were desperately trying to break the Enigma code so that we could find a way of listening in on secret German communications, particularly involving submarines, and learn where they were going to be and when. Turing developed a reputation for eccentricity among his colleagues at Bletchley Park. He was a bit of a strange bird in some respects. He was paranoid about the theft of his coffee mug, so much so that he had it chained to a radiator in his offices. He was a big believer in ghosts, despite being an atheist. He did not believe in God, but he did believe in the immortal soul, and he thought that Hut 8 was haunted. He was also suffering from severe hay fever. He had bad allergies, and he got around this by the expedient of sometimes wearing a gas mask outside during allergy season to protect against pollen. Furthermore, he was obsessed with running and keeping his body healthy, and he would often literally run away from Bletchley Park to meetings in London rather than taking a cab or subway, which meant that sometimes during allergy season, and keep in mind this is at the height of World War II, whenever the Nazis might attack at any moment, many of the folk of London were treated to the terrifying sight of a man wearing a gas mask running at top speed through the streets of the city, when it was really just Alan Turing trying to get to an afternoon meeting. Turing's work would pay off. He would ultimately build a computational machine called the Bombay, B-O-M-B-E. The Bombay was a device that could run coding sequences far faster than a human mathematician. And using that machine, he is able to successfully crack the Enigma code. There's a wonderful book about this called Seizing the Enigma. I highly recommend it. And this was a major factor in the Allied war efforts, because for months we were able to listen in on Nazi communications without the Germans being any the wiser. It was a while before they eventually figured out that Enigma had been cracked, but by that time the Allies had gained significant ground in the war, largely because we knew their next move before they had announced it. Indeed, the cracking of the Enigma was one of the great keys to Allied success in the war in Europe, and without it, the war would have dragged on a lot longer and would have cost a great many more lives. So ultimately, Turing would get recognized for this. He would receive the Order of the British Empire, the OBE, which is the highest civilian honor that can be awarded to a British citizen for his service to the country. But he was not even able to publicly admit it. His work was so secret that he could not even acknowledge the award. It had to be kept classified. But following the war, Turing now had the toolkit he needed, having learned some more mathematical and computational skills during his time at Bletchley Park, to begin building more universal computational machines, and he continued working on that project under contract with the British governments. In 1946, he created the design, well, even before the war was done, he had been working on the design for the ACE, or the Automatic Computing Engine, which executed its first program on May 10th of 1950. The first program that it executed, incidentally, was Ada Lovelace's program for the Fibonacci sequence, written on a punch card way back in the 19th century. Throughout the late 40s, Turing made a number of important developments. In 1948, he actually wrote a chess program for a computer he had not yet finished building. In order to test the program, because the computer didn't exist yet, he actually played chess with a colleague of his, and the colleague would make chess moves according to what he thought was the next best move, and Turing would run the algorithm for the program in his head to determine what the move was that he should make in turn. So he basically made himself into the computer to test out the program before he had a machine that could do that, which tells you something about the kind of mathematical genius he was working with. In 1949, Turing wrote the first programs for a stored program computer. That device, known as the Manchester Mark I, was finally built in 1950, the first computer that had built-in programs that it could execute at will. That same year, 1950, Turing devised the Turing tests, which some of you might be aware of, the test for determining whether or not a machine is artificially intelligent. Turing said that if the machine was being used for communication, if you as a human were talking to the machine in another room, and you had no idea whether the thing that was replying was a machine or another human being, that effectively that device would have met the test to be an intelligent thing. The Turing test is generally considered a little bit inadequate for understanding artificial intelligence in modern terms, but it has served as the basis for CAPTCHA technologies and similar technologies for determining whether or not you are actually a human being on the internet. Now, sadly, Turing's work took a very different turn. Between 1952 and 1954, Turing left behind computer science and began working on a completely different area, computational biology, specifically studying the mathematical biology behind the morphogenesis of plant growth and determining the patterns in the growth of plant leaves using reduction diffraction equations to discover the presence of the Fibonacci sequence in plant growth patterns. Turing's publications in this area were actually not made public until 1992, and they're still considered a vital contribution to computational biology to this day. Now, the reason this is sad is because of the reason he left computer science. And that is one of the great tragedies of 20th century science. In 1952, Alan Turing's home was robbed by a man named Arnold Murray. During the subsequent investigation of the robbery, it came out that Murray had robbed Turing's home in the fallout of a failed romantic relationship between the two men. Homosexuality was a criminal offense under British law at the time. Alan Turing was arrested and charged with gross indecency and obscenity. That's the name of the crime. He was offered a stark choice: imprisonment or chemical castration. Turing, who was claustrophobic and could not stand the idea of being imprisoned, chose chemical castration. He lost his security clearances. He lost his contracts with the British government. He had nowhere to go in the very young field of computer science, and he turned his mathematical genius to plant morphogenesis. He lost himself in books of fairy tales. He loved fairy tales from the time he was a young man, and they were his comfort. In 1954, he was found unresponsive in his bedroom. A copy of a book of fairy tales opened to the story of Snow White beside him, and a half-eaten apple in his hand. There was no autopsy done, but it is generally presumed that Turing committed suicide via poison. In 2009, Great Britain, Queen Elizabeth herself, issued a formal apology to Alan Turing, pardoning him for all crimes and noting that it was the British government's and its response at the time that had committed an act of gross indecency in so ill-treating one of the great heroes of World War II and the father of the computer age. Not so good for Turing himself, I suppose, but I like to think that he gets a little bit of, post facto peace now. Now, let's turn from Turing's story and move a bit broader. Let's go from down here to up there. And up. Space travel has given us access to the moon, but our universe is also, during the 20th century, getting much, much bigger. The discoveries involved in Einstein's general theory of relativity made possible for the first time serious research into the nature and size of the universe itself. It should be understood that prior to the 20th century, most astronomers believed that the entirety of the universe was contained within the Milky Way, and therefore that it was a much smaller, still cosmically large, but still much smaller area than previously thought. Now this view begins to get shaken up in 1912 when an American astronomer by the name of Vesto Melvin Slipher, S-L-I-P-H-E-R, Vesto is V-E-S-T-O. Slipher was born in 1875, died in 1869. Slipher is going to be taking measurements of redshift in spiral nebulae. And he discovers an interesting thing. He discovers that when he measures the redshift of them, they are moving away from the Earth. Redshift is, of course, the Dopplering of light as it moves past a source, giving the impression that it's much longer wavelength than it actually is. Building on that discovery, in 1922, a Russian astronomer by the name of Alexander Friedmann, born in 1888, died in 1953, 1925, is going to derive the so-called Friedmann equations from Einstein's general theory of relativity. Friedman's math supports the view that the universe might be expanding, which you might recall that Einstein himself is rejecting that perspective. But the real breakthrough in all of this is going to come from the work of an American astronomer by the name of Edwin Powell Hubble. Hubble was born in 1889, died in 1953. He was an astronomer working at Mount Wilson Observatory near Pasadena, and later at the famous Palomar Observatory. Between 1923 and 1924, Hubble, using a Hooker telescope, the premier telescope of the day, identified Cepheid variable stars in the Andromeda galaxy and several spiral nebulae as well, demonstrating that this little object that we had thought of as the Andromeda Nebula was in fact an entire galaxy of stars and other bodies, demonstrating that the Milky Way is one of only many galaxies, and that the universe is vastly larger than anyone had previously dared to imagine. Now, building on this discovery, Hubble is going to develop a system for classifying galaxies by shape called the Hubble sequence, which is still in use in astronomy today. And later, in 1929, he is working with another American astronomer by the name of Milton Humason, Humason. Humason was born in 1891, died in 1972. And the two of them discover that the redshift of a galaxy is proportional to its distance from the Earth, an equation known today in astronomy as Hubble's law. This allows us, using the known speed of light, to extrapolate how far away a celestial body is, which even further expands our sense of the size of the universe. Coupled with Einstein's equations, Hubble's law and the Friedman equations clearly demonstrate that the universe is in fact expanding, and that this can be empirically measured and verified, which Einstein, of course, gets a little bit of egg on his face for that and admits that he was in fact wrong about his cosmological constant. So our universe is expanding. That is a definitively known thing. Edwin Hubble is going to be quite a colorful figure in American astronomy for some time. He dies literally taking observations in 1953, has a stroke overnight in his observatory. Interesting little detail about the end of Edwin Hubble's life. He passes away on the night of September 28, 1953. They find him the next morning at the observatory. His wife comes to the observatory to personally collect his body. She puts it into her car, she drives away, and no one knows what she did with it. There is no formal record of the burial of Edwin Hubble. We do not know what happened to his mortal remains. Now, if we have the idea that the universe is expanding, the natural conclusion that we're going to draw from this is, all right, if it's expanding, it must have started from a contracted point, right? That if the universe is getting bigger and bigger, spreading out in all directions, it is reasonable to think there was a time when it was much smaller, much more focused. And this brings us around to the work of a French astronomer, a priest by the name of the Monseigneur Georges-Henri Joseph Edouard Lemaitre. That's Lemaitre. Georges is Georges. Monseigneur, of course, is a title in the Catholic Church. Lemaitre is an astronomer to the Vatican. And yes, he is a priest doing astronomy in the 20th century. The Vatican has long since abandoned its anti-Copernican views, dropped that in the early 1800s. Took a little bit of time, but they got there. And now it sponsors science of its own. To this day, there are Vatican scientists. Lemaitre, who was born in 1894 and died in 1966, based on his studies, concludes that the expanding universe must have begun from what he called a primordial or primeval atom of matter, all matter densely clumped together in one point, which Stephen Hawking would later call the singularity. That primeval atom then exploded, giving rise to the universe that we know now. Now, this idea was mocked by some other astronomers. The American astronomer Fred Hoyle, giving a radio interview in 1950, talked about Lemaitre's idea and scoffed at it and derisively said, "Oh yeah, Lemaitre and his Big Bang." And the name stuck. And of course, Big Bang Theory is going to still be with us today, and has been conclusively demonstrated by astronomy many times over. In point of fact, we know the universe is not only expanding, but its expansion is accelerating, a fact that has still not been fully accounted for and seems to have to do with dark energy. All right, so we talked about some space travel. We talked about the expanse of what space itself is all about. Now, when you start thinking about the Big Bang, you start thinking about the origin of all things. How about the origin of the Earth? How did we get the Earth that we have now? Now, the geologists of the 19th century, people like Charles Lyell, had determined that the world was considerably older than the 6,000 years that had previously been thought. Lyell personally believed the world might be millions of years old, although he never published that number, privately admitting it to friends, because he said the public would never accept something so preposterously high. Now, at the beginning of the 20th century, we are still figuring out details about the age of the Earth and how it got into its current configuration. And there are a number of theories about the shaping of the planets that are popular in this post-biblical worldview in which we're looking for an empirically demonstrable explanation. So let's talk about a few of them. One idea proposed by a French scientist by the name of Edouard Suisse, E-D-U-A-R-D, Suisse, S-U-E-S-S. Suisse was born in 1831, died in 1914. Suisse proposes a theory for the shaping of the Earth that he calls contractionism. The idea behind contractionism is that the planet started off much larger and hotter than it is today, and that over time it cooled. And as it cooled, it contracted and shrank down, and its surface became folded and wrinkled, forming mountains and valleys, that it would shed chunks of matter, which formed ocean basins, and that some of those chunks of matter would then turn into bodies like the moon. Suisse proposed that the continents had once been fused together into a single supercontinent, which he gave the rather whimsical name Gondwanaland, G-O-N-D-W-A-N-A-L-A-N-D, Gondwanaland. Some textures call it Gondwana. But Gondwanaland, he thought, was the supercontinent that everything had once been joined into. He thought it had been connected by now sunken landmasses. He was a big advocate of ideas about lost continents that were now beneath the ocean. Now, Suisse didn't really have any empirical evidence behind his ideas. This was all theoretical. His work was improved upon by a German astronomer and meteorologist by the name of Alfred Wegener, W-E-G-E-N-E-R. Wegener was born in 1880, died in 1930. He's a meteorologist who is most famous for the invention of the weather balloon. But Wegener had also begun speculating on something very uncharacteristic for a meteorologist, the shape of the Earth itself. Supposedly, Wegener's work began in 1910, whenever he noticed that Africa and South America looked on a map like they would fit nicely into each other, like puzzle pieces. He investigated the paleontological and geological environments of both continents and found that similar fossils were found on the western coast of Africa and on the eastern coast of South America, as well as similar flora and fauna that were not seen anywhere else on Earth. This led Wegener to the conclusion that Africa and South America had once been fused together and had separated. In 1915, he writes a book called The Origin of Continents and Oceans, in which he proposes a very famous idea known as continental drift. Continental drift suggests that the continents had all one time been joined together to form a single supercontinent that he named Pangaea, P-A-N-G-A-E-A, for all Earth. He suggested that the continents drifted apart over the floors of the ocean. He didn't have a very solid model for how that happened, but that the continents had slowly drifted apart over time, breaking apart that larger landmass. He said that mountains formed by the crumbling of land whenever, like crumpling a piece of paper, whenever two continental masses smashed into each other. He suggested that rift valleys, like the Great Rift Valley of Eastern Africa, were evidence of incipient breakages, where continents were slowly splitting apart, which we actually know today is kind of true. Now, his ideas were not widely accepted. He was not a geologist, and he was not taken terribly seriously in the field of geology. In 1930, Wegener set off to Greenland in an effort to demonstrate the efficacy of his ideas. He went on an expedition to gather geologic evidence to support his idea. He heads out across the ice shelf of Greenland with an Inuit guide. Never returns. Later that spring, his body is found far out on the ice, wrapped in a sleeping bag with a pair of crossed skis marking its location. The Inuit guide was never found, and we have no idea what happened to Wegener or his guide to this day. Now, this idea was ultimately picked up by a guy who's going to do more with it than anybody else previously, a British geologist and chemist by the name of Arthur Holmes. Holmes was born in 1890, died in 1965, and was, in the early 20th century, the leading expert on radioactive decay, the phenomenon initially discovered with radioactivity through the work of Marie Curie and elaborated with Ernest Rutherford's discovery of radiation in different categories. Holmes developed radiometric dating technologies. He realized, hey, if I have an isotope of a known half-life, I can measure how much of it is present in a thing, I can measure how much of its decay product is present in that thing, and I can back calculate how long it's been decaying, or to put it another way, how old is that thing. So he devises a number of radiometric dating technologies to measure the age of rocks, and by 1910, he is able to put together, for the first time in the history of geology, an absolute geologic timescale. Geologic timescales go all the way back to the works of Lyell and Cuvier, but they were all relative scales, saying, okay, these things are older than those things, but not really able to stick a number on it. Holmes, however, using radiometric dating technologies, establishes an empirical value for the age of the Earth, and finds that it's not hundreds of thousands of years as Lyell published, it is not millions of years as he personally believed, but it is billions of years. That the age of the Earth is approximately 4.5 billion years old, plus or minus 100 million in either direction, a number that is still broadly accepted in geology and astronomy today. That discovery of the vast deep time of our planets, a term that's going to be dusted off from the days of James Hutton, that term deep time, makes us rethink a lot of things. It makes us realize, hey, geologic change can take a lot longer. It realizes evolution has a lot more time to work with. Indeed, this discovery is going to be crucial to the acceptance of evolutionary theories, demonstrating that there's a much, much larger space of time for species to adapt and evolve than anybody had previously thought possible. Now, Holmes, however, is not really interested in the evolutionary side of things. He's a geologist. In the early 1930s, he proposes that the interior of the Earth is not, as Wegener and Suisse before him had thought, slowly cooling over time. Rather, Holmes suggests that the interior of the planet is continuously heated by the decay of radioisotopes in its core, that energy being released directly into the rocky mantle surrounding it, heating it to the point where the rock is melting, creating a thick layer of molten rock, a mantle of magma, surrounding the planet's solid and radioactive core. And as long as those radioisotopes are present and decaying, he says, the planet will continue to be heated from within. He suggests that the land that we see, the land, indeed the seafloors that we see, are all on a thin layer of solid material called the crust, only going down a couple of kilometers at best and floating on top of the denser liquid mantle, like the crust on top of a creme brulee. He suggests that these lighter continental masses are going to be floating on this denser liquid rock and slowly moving around. Because remember, if the planet is being heated from within, by radioactive decay, it's going to be hottest closer to the center, cooler further out, and that means that the liquid in the planet's core, the liquid molten rock, the magma, is going to be circulating. You're going to have convection, where cooler matter is displaced and warmer matter rises up. And that circulating magma, he said, would, over long periods of time, cause slow and gradual shifting of continental landmasses, causing that crust to fragment and break apart, and the different continental plates, as he calls them, to move and shift. He suggests that the supercontinent of Pangaea, he retains the term from Wagner, broke apart into two smaller supercontinents, a southern one called Gondwanaland, and a more northern one that he names Laurasia, Laurasia, consisting of Europe, North America, and Northern Asia. He suggests that these supercontinents then gradually split into the land we know now, and they were still shifting in tiny amounts. And we know this is true. The continents are still shifting. On average, a continental plate moves about 2 centimeters a year. Now, Wagner has introduced some really important ideas. He's given us an age for the Earth, a deep time in which all of this can be going on, and he has demonstrated the possibility of how continental plates might shift. The last piece of this geologic model is going to be introduced by an American geologist named Harry Hammond Hess, H-E-S-S, born in 1906, died in 1969. Hess, in 1960, is going to propose the last really big missing piece of the model, which he calls seafloor spreading. The idea here is that ocean ridges, like the mid-Atlantic ridge down the center of the Atlantic Ocean, are produced when continental plates shift apart from each other, creating a fissure through which magma can bubble up from the core, touch the seawater, and harden, forming new seafloor all the time, slowly pushing the continental masses further and further away from each other. He said that what would happen here is that continental plates, when they came into contact with other ones at fault lines, would either slide beneath them, a process called subduction that would gradually push the plate back down into the planet's interior, or that they would crumple up against each other, much like Wagner had thought, forming mountains, or that possibly they could lock together, where pressure would build up at the places where they were rubbing and eventually be released in the form of earthquakes. Hess also suggested a very thin crust, only between 35 and 5 kilometers thick, 5 to 7 kilometers thick beneath the oceans, as much as 30 to 34 kilometers thick on land. And then the mantle, he said, was much thicker, averaging about 2,900 kilometers deep. Hess's model provides explanation for earthquakes, volcanic eruptions, and Atlantic ridges, and explains how it is that the plates might spread apart. Two Canadian chemist named Daniel Mackenzie, born in 1942 and still alive, and a Cambridge chemist by the name of Robert Parker. But Mackenzie and Parker are going to collectively propose the term plate tectonics, T-E-C-T-O-N-I-C-S, as a way of explaining and synthesizing all of these ideas into a singular theory for explaining the formation of our planet's crust, its oceans, and how it changes over the course of long periods of geologic time. That term plate tectonics was coined in 1967, and the general model is still in use in geology today. So, we come at last to a place where we've been surveying a wide range of scientific domains. We've hit some geology, we've hit some astronomy, some computer science, some nuclear science, some relativity, some important technologies along the way. We have neglected one important area. Let's talk biology. And nothing is perhaps more important in 20th century biology than the fourth great scientific revolution. And this is not a thing your average science historian is going to say. Most science historians like to talk about the three great scientific revolutions, the Copernican, the Newtonian, and the Darwinian. I am about to offer you the fourth great scientific revolution, the DNA revolution. And I would argue future science historians are going to look at it as such. We're still in the midst of it, and therefore it's probably not being discussed much under those terms, but make no mistake, it is a revolution on par with those. The discovery and understanding of DNA has changed everything about the biological and medical sciences, from our understanding of inheritance to our understanding of evolution to how we approach and treat diseases. So I feel like a good place to end this class is to tell the story of our ultimate inner space, and to say a little bit about the life molecule that drives all of us, all living things, in fact, and indeed non-living things like viruses too, and say a little bit about how we came to its understanding. Because the DNA story is not only the beginning of a great scientific revolution, but it's a very fitting story in a lot of ways to end this course, for reasons that should become clear. Now, I have to begin before the 20th century for this, because DNA was actually discovered way back in 1869. The original discoverer of DNA was a Swiss hospital physician by the name of Friedrich Miescher, M-I-E-S-C-H-E-R. Miescher was born in 1844, died in 1895. He was a hospital physician in Zurn, Switzerland, and he was doing studies of pus on the surgical bandages of patients. He's a 25-year-old physician just getting started in his career. As he's examining the chemical contents of that discharge from surgical bandages, he notes proteins, carbohydrates, and lipids. But he also finds a new kind of organic molecule, a fourth category of basic biomolecule not previously documented. He didn't know what it was for. He knew he was always finding it in the nuclei of cells, and therefore he gave that molecule the name nuclein, N-U-C-L-E-I-N. And from that we derive the modern term nucleic acid. Over the next few years, Miescher and his students studied his nuclein, discovered that there seemed to be more than one type of nucleic acid, but they never determined what they were for. Now, it should be understood that throughout the late 19th and into the early 20th century, much of the energy in biology was dedicated to the question of exactly where hereditary information lived. Darwin and Mendel, with their respective hereditary theories, both knew that there had to be a hereditary molecule, some sort of chemical agent that was transporting genetic data from one cell to the next and from parents to offspring. Something in the cell was getting passed on. Nobody was clear what that something was. Now, by the end of the 19th century, several independent biologists have discovered the phenomena of mitosis and meiosis, of cell division, and noted that during cell division, the chromosomes of the cells are condensed, separated into two groups, and each cell gets an equal number of them, suggesting that the chromosome is the agent of heredity. Now, for those of you who aren't biological folks, a chromosome basically consists of DNA tightly wrapped around packaging proteins called histones, like thread around a spool. A chromosome is a convenient way of moving DNA around within the cell and storing a lot of DNA in one space. Now, by the late 19th century, we're largely convinced that the chromosome is the agent of heredity. However, most biologists at this time are looking at the wrong part of it. They think that the genetic data is stored not in the chromosome, not in the DNA, but rather in the histone. They think that the packaging protein is the site where the genetic data is stored. The reason for this is quite frankly because proteins are way more complex biomolecules than DNA is, and therefore it was presumed the protein must be the site of storing complex data. DNA, they thought, was basically a sort of scaffolding, a protective molecule wrapped around and supporting the delicate information-bearing histone proteins within the chromosome. Now, this is, to put it bluntly, wrong, and we are not really making a lot of headway with investigating the histone component of a protein in an effort to find out exactly how it's storing genetic data. Throughout the early 20th century, we're making a lot of important discoveries in genetics. People like Thomas Hunt Morgan and Ronald Fisher, whom I mentioned in our Darwin discussion, are bringing together Mendelian genetics and Darwinian inheritance to build the modern synthesis in biology. We have a good explanation for heredity, but we still don't have a hereditary vehicle. We still don't know where the information lives, and our efforts to derive it from histones are proving to be fruitless. Now along comes another fellow, a Lithuanian biochemist by the name of Phoebus Aaron Theodore Levine. Phoebus, P-H-O-E-B-U-S, Aaron with two A's, Levine, L-E-V-E-N-E, often went by P.A. Levine. Levine was born in 1869, died in 1940, native of Lithuania, fled his home country in the 19-teens to escape anti-Jewish pogroms when Lithuania was conquered by Russia. He took up residence in New York and eventually became the head of the Rockefeller Institute, which remains a significant library in the biochemical sciences to this day. He's the head of biochemistry at Rockefeller, and Levine, throughout the 1920s, did a serious investigation of DNA in an effort to find out if, in point of fact, this long-ignored molecule might be the hereditary molecule. Now, Levine, in the course of his research, learned some important things about DNA. And those of you who are bio folks are going to know a lot of what I'm about to say to you. Levine is going to discover that DNA is a polymer, a chain of smaller molecules, that those smaller molecules are called nucleotides. He discovers and describes the chemical structure of nucleotides, and he discovers that nucleotides come in 5 basic types: adenine, guanine, cytosine, thymine, and uracil. Or those of you who know your genetic alphabet, A, G, T, C, and U. He discovers that every nucleic acid is a polymer of nucleotides joined one onto the next. He discovers how they are linked together through a phosphate molecule bonded to a hydroxide molecule, forming a phosphodiester bond and linking them in a long vertical chain. Furthermore, he distinguishes between DNA and RNA as deoxyribonucleic acid and... Sorry, folks, just spilled my pop. But anyhow, though, so Levine has discovered the basic chemical structure of DNA. He's distinguished between DNA and RNA. When I say structure of DNA, he's discovered the basic makeup of it. He has not learned the structure of the molecule. He has learned what it is made of, and he has learned how the polymer forms. All of this is really important. But Levine, on the basis of his research, ultimately concludes that DNA is not the hereditary molecule. He says, well, look, it only has 5 basic letters in its structure. It's too simple to encode the complexity of genetic information. It doesn't have enough variability to encode that kind of complex data. Therefore, he said, proteins, which have 20 basic amino acids as opposed to only 5 basic nucleotides, he said proteins must therefore be the genetic molecule, that they have enough complexity to encode all the details of life. DNA, he said, and RNA do not. Furthermore, Levine came to the incorrect conclusion that DNA was a repetitive sequence. He had accidentally happened, just by luck of the draw, to zero in on a section of DNA that was a repetitive sequence in his research, and he concluded that the whole molecule was like that. So Levine dismissed DNA as the genetic molecule and suggested we go back to looking at proteins. Now, this persisted for a while, and throughout the 1930s, there were a lot of investigations, but nothing was bearing fruits. And increasingly, biologists were beginning to think maybe there's something more we are missing here. Now, a big but largely unnoticed breakthrough is going to be made in 1944 by an unassuming Canadian-born American bacteriologist by the name of Oswald Avery, A-V-E-R-Y. If you are picturing in your head a man named Oswald Avery, you are correct. Little tiny unassuming guy, little spectacles, little bald fellow, quiet, shuffled up to his podium, gave his papers, shuffled back away. Nice guy, friendly guy, mild-mannered, and probably the most brilliant bacteriologist of his age, and certainly the world's foremost expert on pneumonia. Now, he was doing an experiment, and this was building on the work of a British doctor who had been killed in the Blitz during World War II, a fellow by the name of Dr. Griffith, who had determined that there was more than one kind of pneumonia, some of which were more lethal than others. Now, Avery did an experiment in which he took 2 varieties of pneumonia bacteria, One variety that was a more lethal bacterium, the S-type pneumonia, he called them, and one variety that was less lethal, that he called the R-type. The S-type, when injected into mice, would cause them to get sick and die. The R-type, when injected into mice, would cause them to get sick, but they would recover from the pneumonia. It was a milder strain. Now, Avery, based on the previous work of Griffith, had shown that you could heat treat the bacteria and kill them. Avery heat treated his S-type pneumococcus bacteria and mixed it with living R-type ones. The heat-treated S-types died. He mixed them up with the living R-types, and he found that after that, the R-types changed. The R-types became lethal. Moreover, when they divided and reproduced, they produced lethal progeny. Avery concluded that there must be some kind of what he called a transforming principle that was present in the S-types, was released from their cells when they died, was slurped up by the R-types that somehow changed their genetic composition. Basically, the R-type bacteria were consuming some kind of chemically based genetic information from the S-types, which changed their nature and caused them to become more lethal. Those of you who know your bacterial genetics realize what I'm talking about. I'm talking about plasmids. But Avery didn't know that. Plasmids hadn't been discovered yet. So Avery sets up a very clever experiment to figure out what's going on here. He does this whole operation again. He takes S-type bacteria, heat treats them to kill them. But then he divides his sample in three. One portion of his S-type bacteria he then mingles with a protein digesting enzyme that breaks down any proteins present in the sample. One he mixes with an RNA digesting enzyme, and one he mixes with a DNA digesting enzyme. Then he exposes his three samples to three separate populations of non-lethal R-type pneumonia. What he finds is that the bacteria in the samples exposed to DNA digesting enzyme do not change. They do not become lethal. But the ones in which the RNA and the proteins were digested, those transform. Those become lethal. On that basis, Avery concludes that DNA must be the transforming principle, the vehicle for hereditary transmission. Sadly for Avery, his paper does not get a lot of attention. The simple fact of the matter is he is the best trained person in the world in pneumonia at this point, and there's nobody else who is good enough at what he does to independently verify his research. His papers did not get a lot of traction, combination of that and a dug-in belief that proteins must be the vehicle of genetic information, and Avery's work is largely overlooked. Later, he does live long enough to see his work recognized. He survives till 1955, sees Watson and Crick publish their famous papers, and sees that his DNA research is vindicated. Sadly, however, Avery never got any formal scientific recognition for this rather important achievement. Some have called him probably the most important biochemist to not get the Nobel Prize, given the vast significance of his discovery. Now, Avery's work was finally proven to be true with another experiment done in 1952. Actually, we're skipping ahead here a little bit. We're going to get to that in a minute. Okay. So Avery's work is out there. Not a lot of people are taking it seriously. But DNA is beginning to be looked at as a more and more serious candidate for the genetic molecule. In 1950, an Austrian biochemist by the name of Erwin Chargaff, Erwin, E-R-W-I-N, Chargaff, C-H-A-R-G-A-F-F, comes along. Chargaff was born in 1905, lived all the way till 2002, and remained pretty active up until his death. Chargaff was not only a biochemist, but he was a popular science writer. Wrote a lot of books about science for the benefit of non-scientists. Chargaff was a good communicator. He had the rare combination of talent in science and talent with the written word. He was good at speaking to non-scientists and explaining things in down-to-earth language that people could understand. Did not hurt that he was handsome and charismatic, a really good public speaker, and he was kind of full of himself. Erwin Chargaff, at his public talks on scientific topics, afterwards would pass out signed headshots. And if you go on Google and you search for Erwin Chargaff and do an image search, first thing that'll come up will be one of his signed headshots with his movie star kind of looks. So a little bit of an ego on him. But Chargaff was also a decent biochemist. He never cracked the nut of DNA, but he did learn some important things about it. He discovered two basic things. First off, he discovered that DNA was different in every organism he studied, that it was not a repetitive sequence as Levine had thought. Making it different in every organism made it a lot more credible as a potential genetic molecule. Secondly, he discovered that there was a pattern in DNA. He realized that only 4 of the 5 nucleotides identified by Levine were present in DNA. A, T, C, and G. U was only present in RNA. And he found that there was a distinctive pattern in DNA. No matter what organism he looked at, the amount of A, adenine, in the DNA was always equal to the amount of thymine, T. And the amount of guanine, G, was always equal to the amount of cytosine, C. The proportions varied from one organism to another, but it was always in the same ratios. A always equals T, C always equals G. We refer to that to this day in biology as Chargaff's rules. And Chargaff knew this had something to do with the structure of the molecule. He never quite worked it out. He did later meet with Watson and Crick, tell them about his ideas. Their information was quite crucial to them solving the DNA puzzle. More about that momentarily. And Chargaff, for the rest of his life, remained bitter that he never got a Nobel Prize acknowledgement for his contribution to discovering the structure of DNA, although he himself never figured out what the significance of that pattern was. Now, the last final proof that DNA was in fact the hereditary molecule came in 1952 with the work of an American biologist by the name of Alfred Hershey, born in 1908, died in 1997, and his young graduate assistant, a woman named Martha Chase, born in 1927, died in 2003. Hershey and Chase were studying tobacco mosaic virus, and they were endeavoring to figure out exactly how this virus worked. Hershey was a virologist more than anything else, and in this time, nobody really knew much about how viruses infected cells. So Hershey and Chase were endeavoring to find out how this worked, and they came up with a rather brilliant exercise. The Hershey-Chase experiment is called one of the most famous experiments in the history of modern biology. What they did is they said, okay, we know that DNA always contains phosphorus. Proteins never do. We know that proteins contain sulfur, and DNA never does. Therefore, they said, we can use phosphorus and sulfur to label the components of a virus, because a virus is a very simple non-cellular chemical structure. All it consists of is going to be a little bit of DNA or a little bit of RNA for some viruses, like the coronavirus we're all worried about now, wrapped up in a coating of protein called a capsid. So protein and DNA, that's all you got to work with in tobacco mosaic virus. One or the other of those things had to contain its genetic information. Hershey and Chase get the clever idea of radio labeling the two parts of the virus by culturing the virus with a radioisotope of phosphorus and a radioisotope of sulfur, so that you could see which component of the virus was where on the basis of the radioactive isotopes incorporated into them. They did this, and then they allowed their viruses to infect cells. They discovered when this happened that the radioactive sulfur never entered the infected cell. The capsid of the virus attached to the outside of the cell and injected the DNA. Later, viral progeny extracted from the cell were proved to have the radio-labeled molecules within them. As such, clearly demonstrating that it was the DNA component of the virus that had infected and penetrated that cell, and by extension, that DNA was the hereditary molecule. Hershey's work had actually been setting out to discover how viruses infect cells, but along the way, he and Chase definitively proved that DNA was the vehicle for hereditary information. Ultimately, Hershey would receive a Nobel Prize for his accomplishments some decades later. Martha Chase was not named in that prize. She had left science altogether by that time. In fact, Martha Chase had a scientific career that did not last for 10 years after the famous experiment that still bears her name. She retired from science altogether, became a housewife, and died of early onset Alzheimer's in 2003. And one of the little pet projects I eventually want to explore as a science historian is to track down her living relatives and find out if they can shed any light on exactly why she quit science after engaging in something that very important. And it wasn't because she wasn't named in the Nobel Prize, because she quit long before that Nobel Prize was even considered. So, we know DNA is the hereditary molecule, and the race is on. Anybody who's anybody in biochemistry by the early 1950s is trying to figure out how DNA does the thing. We know DNA is the hereditary molecule now. We need to know how it codes information. We need to know its chemical structure. Lots of folks are working on this. Erwin Chargaff is working on this. An American by the name of Linus Pauling. You might have heard of Pauling, P-A-U-L-I-N-G. Linus Pauling is the vitamin C guy, the guy who told you that vitamin C makes you feel better when you're sick, although it turns out he's not entirely right about that. But in any case, though, lots and lots of folks are working on this puzzle. Now, if you ask the average person, who figured out the structure of DNA? The answer you will usually get is a pair of names. An American biologist by the name of James Dewey Watson, born in 1928, still living today, and his British colleague, a biochemist named Francis Henry Compton Crick. Crick was born in 1916, died in 2004. Watson and Crick, those names are virtually synonymous with DNA. And hopefully those of you listening already know that the story is not quite that simple. But let's begin there. James Watson was an American biologist trained at the University of Chicago. Primary area of expertise of all things was ornithology. Francis Henry Compton Crick was a biochemist trained at Cambridge. Both of these men were early in their careers at this point. Both of them landed postdoctoral fellowships at the Cavendish Laboratory. Now, they happened to be assigned office space together because both of them were working on the same project. They were both assigned to work on tobacco mosaic virus, which you might recall is the same virus that Hershey and Chase were working with. Now, Watson and Crick got to chatting, discovered that both of them had a mutual interest in the hot topic of biology of the day, which was the structure of DNA. They were familiar with Hershey's work from their work with tobacco mosaic virus, and therefore well aware of the fact that DNA had been demonstrated through his research to be the hereditary molecule. So Watson and Crick took it upon themselves to discover the secret of DNA and began investigating the molecule. I should point out this was not their job. They were not assigned to be working on DNA at the Cavendish Laboratory. They were supposed to be working on tobacco mosaic virus. In fact, they were upbraided by their superiors on more than one occasion for using Cavendish Lab resources in a private personal project. Nonetheless, they persisted, trying to build a molecule of the DNA. Those of you who are biology folks would have thought some of their models were kind of funny. For a while, they thought it was a three-stranded molecule. For a while, they thought that the sugar backbones went on the inside and the nitrogenous bases pointed outside. They've learned some really important things about the molecule. They learned a lot of things about how it comes together, about its shape and its basic chemistry, but they had not yet deduced how it was structured. Now they're working on this. They're not supposed to be, but they're continuing. Someone else in London is supposed to be working on this. Across town from Cambridge, at King's College London, the DNA puzzle is being attacked by a scientist by the name of Rosalind Elsie Franklin. R-O-S-A-L-I-N-D, Rosalind Elsie Franklin. Franklin was born in 1920, died in 1958. We're actually, is today the anniversary of her death? April 16th? Not quite there yet, a couple days. But Rosalind Franklin was a young Jewish scientist from England. She had trained for a while in France and came back to England to do biochemical work. And she was one of the only women who was making a serious go of it in biochemistry. She had gotten a PhD in the field. She had become known for her research on coal. Indeed, a lot of her work on the chemistry of coal is still cited today. But at King's College, she was not working with coal. At King's College, Franklin was working with DNA. She was an expert in a technology known as X-ray diffraction, or X-ray crystallography, which is basically a method of using X-rays to photograph molecules embedded in a crystalline matrix. You can't photograph a molecule with standard light photography because a wave of light is bigger than the diameter of a molecule and can't be reflected from it. X-rays are smaller. And so Franklin was applying her knowledge of X-ray crystallography to photograph DNA in an effort to determine the structure of the molecule. She was making good headway with her research. And in fact, Watson and Crick attended a talk that she gave on her work and were quite impressed by it. Now, Franklin had a colleague by the name of Maurice Wilkins. Wilkins was born in 1916, died in 2004. And Wilkins badly wanted a piece of the DNA pie. Now, Wilkins was good enough to be head of a lab at King's College, but he was not the guy who was going to make great, amazing DNA discoveries all by himself. And so Wilkins was constantly pestering Franklin to get in on her project. She had a lab assistant already, a fellow by the name of Raymond Gosling, Gosling, born in 1926, still living today. And they were making good headway, but she did not want Wilkins on board the project. Franklin was all too keenly aware of her position as a woman biochemist in the 1950s, at a time when science was still largely viewed as a boys' club, and in which women scientists had to work very hard to prove themselves. Wilkins had little respect for women in the laboratory and made little pretense of that. He was trying badly to shoehorn in on her project, and Franklin knew that if Wilkins was allowed on board, he was going to co-opt her research and that she was never going to get any kind of progress or acknowledgement for it. So she rebuffed his efforts to involve himself in her project. Wilkins got pissed about this. Without Franklin's knowledge, he slips into her laboratory, removes X-ray diffraction photographs of the DNA molecule, including the famous photograph 53 that you can see online, and passes those photographs on to Watson and Crick. Says, hey boys, I heard you're still working on your little DNA project. Here's something that might help you out. Watson and Crick looked at Franklin's images, combined them with their own discoveries, and together made the breakthrough. Now make no mistake here, folks, when this is reported, and a lot of times this is a story that wasn't told until really recently. Rosalind Franklin has finally undergone a bit of a renaissance, getting acknowledgement for her achievement. For the longest time, it was forgotten about. Sometimes the way it's reported nowadays is that Franklin did all the work and Watson and Crick just stole it. In point of fact, Franklin had made some vital discoveries that Watson and Crick had not. Watson and Crick had made some vital discoveries Franklin had not. And Watson and Crick integrated that data and discovered what they were missing. In May of 1953, 5 papers were published in the journal Nature. An entire journal was dedicated to these papers, entire issue of the journal, I should say, detailing the chemical structure of DNA. The very famous structure that you all know today, the 2 polymers wrapped around one another in the spiral staircase pattern that James Watson called the double helix. The 2 strands held together down the middle by hydrogen bonds between their nucleotides, A always pairing with T, C always pairing with G, just as Chargaff's rules suggested would be the case. A lot of folks know that those papers had 3 authors, not 2. James Watson, Francis Crick, and Maurice Wilkins, whose sole contribution, of course, was in passing on Franklin's Perlewind data. Studies of Rosalind Franklin's notebooks indicate that she was basically at the discovery, that had she had another month or 2 to work, Franklin would have had the structure of DNA down. She would have published herself within a couple of months. And had she had those couple of months, she'd be the only name we'd be talking about in terms of the discovery of DNA. Watson and Crick would be a footnote in history. But Franklin never got that opportunity. Franklin, in fact, never knew her work had been stolen. In fact, she wrote a very glowing review of Watson and Crick's papers following their publication. And Franklin herself never really had the opportunity to show what else she could do. Because by 1953, she was already in the early stages of ovarian cancer. She died in 1958 at the age of 38 years old, and died never knowing that her research had been incorporated into the most important biological discovery of the 20th century. In 1962, Watson, Crick, and Wilkins received the Nobel Prize in Medicine for the discovery of the structure of DNA. none of them saw fit to mention Rosalind Franklin in their acceptance speech in Stockholm. Her story was brushed under the rug. It was easy to do, quite frankly, because she was a Jew and a woman, at a time when being either of those things in England was not terribly popular, and being either of those things in the sciences was not terribly popular. It was the misogyny that pervaded more than anything else. And Rosalind Franklin was on her way to becoming a footnote in history. Now, from here, Watson and Crick both went on to illustrious careers of their own. In 1957, James Watson laid out the so-called central dogma describing gene expression from DNA to RNA to protein. Francis Crick went on to describe the codon, the three-letter unit of genetic information that eluded Levine when he thought that individual letters were the unit of coding. Later, in 1988, James Watson became the head of the Human Genome Project at Cold Springs Harbor Laboratory in New York, labored on it for years, and in 2000, he partnered up with another biologist, J. Craig Venter of California, and the two of them collectively finished sequencing the human genome, identifying the locations of all the genes present in DNA of human beings, a discovery that has continued to revolutionize the way we do medicine. Maurice Wilkins never really did anything else important. Now, we would not know this story if not for the efforts of Raymond Gosling. Raymond Gosling was aware of what had happened to Rosalind Franklin. He made an effort to make sure that her story was told. And as a result, we know who she is. We know what happened, and we know how her data was stolen. One of the cardinal sins of science, I'm sure you all know by now, is plagiarism. Now, second only perhaps to falsifying your data. Now, before they died in 2004, both Francis Crick and Maurice Wilkins admitted to what they had done, confessed to their theft of Franklin's data, expressed regret for their ill treatment of her. Francis Crick said you should never mention him and James Watson in the same breath in which you do not also mention Rosalind Franklin, because her contribution was just as important as theirs. James Watson, still alive. James Watson is now in retirement. He was 92 years old. He continued doing active research until not all that long ago. In fact, he held his position at Cold Springs Harbor Research Laboratory until as recently as 2013. Watson has never admitted any wrongdoing, despite the fact that that Crick and Wilkins have both fessed up to what they did. Watson refuses to this day to acknowledge Rosalind Franklin's contribution. He describes her in his book, The Double Helix, as Dear Rosie, a diminutive nickname that she hated. He talks about her being a clever girl, but not anyone who was going to make great discoveries. He is continually disparaging of her, and not only of her, but basically of every woman in the sciences. James Watson is a misogynist. James Watson is a racist. And in 2013, he lost his position at the Cold Springs Harbor Research Laboratory after giving an interview on the anniversary of the discovery of the structure of DNA, talking about where things have gone since then and the possible future of genetic science. And in that interview, he posited the idea that the persistent political and economic problems facing the continent of Africa are a consequence of genetic inferiority on the part of native Africans. He followed that little gem up by saying, any of you who have had an African-American lab assistant know what I'm talking about. Needless to say, that particular view, being expressed by one of the men whose discoveries proved that that's not how this works, is especially monstrous. And the biological sciences, fortunately, did not take it lying down. James Watson was essentially blackballed from biology. He resigned his position at Cold Springs Harbor Laboratory a month later, and has basically been in this angry, growly retirement ever since, sending out boo-hoo tweets about how he had to sell his Nobel Prize medal in order to keep on living in the style to which he was accustomed, and occasionally growling about how he's apparently working on some secret biology project in his basement that's going to show us all. So he's gone full-on mad scientist in his retirement. And frankly, he's not involved anymore, to which I say, good riddance. Rosalind Franklin is now enjoying the reputation that she deserves. And whenever you're telling the story of DNA, don't just say Watson and Crick. Say Franklin, Watson, and Crick. Let's put her first. I think she deserves it. And I think this is an appropriate point to end the lesson and to tie off this course, because it brings us back around to something that we've been talking about since the beginning, since the very first days of science in Miletus, when the natural philosophers like Thales and Anaximander began discussing principles of reason governing the natural world. Science then was largely the game of rich white men. I wish I could say it wasn't. We're getting better. As of this last year, there are more women going into medicine and biology than men. That's a new thing. Women still have to fight uphill battles in the sciences. There are still plenty of grunting Cro-Magnon men in laboratories who don't think that a woman has any place in one. And to all of you listening who are going into the sciences, I offer you this charge. If you are a woman in the sciences, I'm sorry, you're going to have to deal with this bullshit at some point. Don't take it. Make them explain themselves. Put them on the spot. Make them uncomfortable. Make them squirm. Do not let them get away with saying you are less. To all the men listening to this, my charge to you is do not perpetuate this bullshit and use your privilege. You got it. Use it to make sure that this doesn't happen. Use it to make sure that the Rosalind Franklins of the world get their just dues. Use it to make sure that we stop this nonsense and that we are the last generation of scientists to be plagued by misogyny. And I think that is an appropriate time to end this. I hope you all enjoyed this lesson and this series of lessons. I bid you all good night.